Well, all right, so let's get into a little bit of an application problem, right? We study math for a variety of reasons. Some of you just have to take classes, and some of you want to be engineers, and maybe some of you just like solving for X. Who knows? Maybe your counselor just decided to throw you in this class. I don't really know. But it turns out that there's some really useful stuff with this math stuff we learn. Like all these polynomials. So far we haven't really, it's like, why are we examining some curve, right? It doesn't really, what's the point of this? Well, it actually turns out that it's really useful. And here's one application problem. Let's suppose there is a 24-inch square piece of cardboard just laying there. And I'm challenging you to construct a box, right? So take it from the two-dimensional square piece to a three-dimensional box with a square base, and it's going to have maximum volume. So that word maximum should be familiar to you. We've done maximum with graphs before. So before we get too far, let's just start to generate a little picture, right? So this is kind of an engineering physics, maybe not physics problem, an engineering problem. One way to solve those is just draw a picture. So let's draw a picture with a 24-inch square piece. I guess I should have been more specific when I rewrote this problem. Is 24 inches is the square, right? 24 inch by 24 inch, right? So let's see. Let's construct that, and I'm just going to draw. It doesn't matter. Let's just got to be square. So let's see. It doesn't matter. Because right now we're just trying to make sense of this problem. So I need to take this square piece of cardboard that's 24. So this distance here, ooh, that's terrible. It's 24 inches, right? And I need to make a box out of it. So I need to like fold up some stuff. Well, the best way to do that would be to and I need the base to be square, right? So I need the inside to be square, and I need to cut in some corners so that I have a square base. So let's just kind of do that. So if I cut in here and here, I'm just picking the distance here. I don't know exactly what the distance should be. If I cut in there, right, if I had some scissors and I cut in that distance there, the inside, this would be the bottom, so these would be this, that would be a side, that would be a side, these would fold up, right? So the fold would be there and there and there. This area right here would be the base. That would be a square base. And these are arbitrary, right? So I don't know how far to cut in, because what my goal is to maximize the volume. So I haven't worked this problem out ahead of time. I'm just kind of going with it. So let's just kind of think about this. So when I said arbitrary, that means it could be any distance, right? I mean, certainly I couldn't cut in, like if I move this line backwards or forwards, I could cut in 1 inch, I could cut in 2, 3. I certainly wouldn't want to cut in 24 inches. That wouldn't make much sense, right? I guess I couldn't go past the halfway point, because then the other half would come in. So that's just kind of making sense of the problem there, right? I mean, if I come in past 12, then it wouldn't work. I mean, even if I did 10, let's say I came in 10 inches here and 10 inches there, that would leave a remainder of what, 4 inches in between there? And that wouldn't really work too well. That certainly wouldn't make a very good looking, or maybe it would. Maybe that would be the maximum amount. I have no idea. But what we're going to do is let's label these. So I don't know how far in I'm going to cut. So this distance here, which would be this distance, is X, right? And these are all square cuts. So this would be the same logic. So X and X, and that's because we need to make this base a square. So all of these distances here are all the same. They're all X, right? And so the only number we're given is the length of one side of this square, 24 inches. And what I need to do is I need to think of what's the volume going to be. So the volume of a cube, right? So the volume is going to be the area of the base times the height. Well, the height, and when I fold this up, that's just going to be X, right? So this is going to be area of the base, which will be this distance here times this distance here, right? Which should be the same because it's a square, times this distance. So this X will be the height. So it's volume of a cube is going to be the area of the base times the height. So let's see. So this is going to be, let's say, volume in terms of X. It's going to be the height times this times this, which is just the same thing. Well, that's going to be squared. So how can we represent this area right here? This area right here. So let's see. That's Well, it's definitely less than 24. It's not 24, so it could be anything less than 24, right? So it's 24 less 1 distance of x, 2 distances of x. So this right here is going to be 24, the distance 24 minus 2 times x. Now the reason that is because here's distance x, here's distance 1x, 2x. So subtract 2 distances of x from the 24, and that's the one side length of the square on the base. So 24 minus 2x. And so what we have here is we have an equation. So this is x to the first power times the quantity 24 minus 2x, all of that squared. So what we would need to do then is we would need to examine this polynomial. So again, we've transferred from this really contrived problem with this cardboard box where you need to maximize the volume, and we've created a polynomial because this is the equation of the volume, and we need to investigate this. So as you might expect, we're going to investigate this and we're going to look for a maximum. So, and I can tell you just from looking at it, this is actually going to be a cubic because this part's squared and this part's to the first power. So we're going to end up with an x cubed somewhere. And I don't know if you remember the parent graphs, but x cubed sometimes look like this. So what we need to do is we need to investigate that, what that looks like on a graph, see what this ends up looking like, and we need to look for a maximum, right? And we need to interpret this a little bit. So we can't just, all of these points on this line aren't necessarily going to make sense in the context of our problem. So we really need to make sure it makes sense. Kind of obvious, right? Well, one tool you might have if you're just doing this problem is your calculator. I've got this old TI-83 Plus, so you might be thinking, all right, well, I'll just graph that. So what's x times 24 minus 2x squared? What's that going to look like? Well, if I just hit graph, let's see what my... didn't look like it did anything. When I hit graph, this thing was thinking. The reason is because the scale of this, it's not on there. And one of the hidden skills that makes this difficult is understanding that I need to mess with the window. So it's kind of an old Algebra 1 trick, maybe Algebra 2, maybe, hopefully you've learned this, but understanding this part will really help. These graphs don't really look that great, and that's why I showed you Desmos. Desmos is a great tool to use. So I would transfer now to go to Desmos to try to interpret what that looks like. If you wanted to use the calculator, what you need to do is you need to look at the window. And so one thing you might be thinking is, all right, well, where are the x-intercepts? That might help guide you. So you want some critical points. You could also expand that. You could look at that in a standard form to look at where the y-intercept is. You could look at where the x-intercepts are. The x-intercepts are going to be at 0, and it looks like whenever 24 minus 2x equals 0. So that would be what? Let's see, that would be 12, right? So that means the window for the x would be, let's go from 0 to maybe let's go to 15. Let's see if that helps at all. All right, so we saw that part of the graph is there, and since we know something about the family of functions that we're working with, it must go up like that, right? So then I just need to expand the window up. So how far up should I go? I mean, I have no idea. Let's go from 0, the minimum for 0, to let's try 100, see if that changes anything. Not really. I'm getting better. It looks like, man, that looks like it goes way up. So let's try, what if we tried 1,000? And this is scale, let's count by, I don't know, tens. I don't know if it's still going to look pretty bad. Okay, we're getting better now. All right, we're getting there. So let's go 1,200. Let's count by hundreds. Well, all right now. Now everything I just did, you might be going, well, I wouldn't have known to do that. Well, that's because I've done a lot of these problems. And so what it's going to take is a lot of practice. From here, you're going to want to look at this graph and interpret it. So at this point, I'm going to switch over to Desmos and explain this a little bit better because I think it's going to be a lot easier. You could still maintain this from this point. In fact, your graphing calculator will tell you a maximum point, but I'll just pick up from here on Desmos. All right, so here we are in Desmos, and I've pulled up a blank one. And so what I'm going to do is I'm going to graph what we just did in the graphing calculator, my TI-83. So I've got this, and this is going to equal, what do we have? X times 24 minus 2x squared, right? Oh, I think that was all we had. Now, as I graph that, if you were to just start off with it, it would look, oops, I actually did that wrong. The squared is not supposed to be there. It's supposed to be here. Okay, so just like the graphing calculator, That doesn't help us a whole lot, does it? And maybe you might be on your phone, so maybe you're trying to use your fingers and you're moving it around. You're like, man, I'm scrolling out here, and then your graph's just getting really messed up. It just looks like a mess right now. I mean, we have no way. It's just pretty awful. Maybe you figured out how to adjust that, but you essentially need the same skill on here, right? You need to be able to look at the graph settings and change them. So you really need to be able to investigate that function and go, okay, I need to go from 0, and I need to go to, let's say, 14 like I did before. And then on the y-axis, I need to go from 0, and I know the maximum's way up there. I mean, we already did this. We already talked through it. So let's just say 1200 again, right? Oh, this one said 6. I wonder why I did that. All right, so there's that part, and then you can move it around again. So we've got a much better looking graph, just like we did before. And from here, we can kind of examine it a little bit more. I think one final hint that I didn't explain on the graphing calculator that I can explain here, on Desmos, you can create any equation and look at the table. And that actually might be the best place to start to get some intuition around it. I can't believe I didn't tell you that before, but if you click this little edit list, you just click on convert to table, and it'll take that function and make it into a table. So it actually plots these points for you. As you can see, it plotted 0, 1, and 2. You can see them in there. And if I just click over here and hit enter, it'll continue to plot those points all the way across. Now, this is much easier on a computer. So if you're working at home and you have either a tablet or something, or maybe a really big phone, you can use that. But you could do the same thing in your graphing calculator. You just hit the second function button, and then you hit graph, and you can look at the table and start to investigate, right? And then from there, you'll be able to see, like, wow, this graph at x equals 4, it's 1024. And that's what we want to interpret. We're trying to maximize the volume of that box, and we need to make sense of this equation that we came up with. Now, I don't know if you remember, but the x value was how far we're cutting in on that box. And so, as we said, if we cut in 12 inches, that's going to make the volume of the box 0, right? Because that would cut half the box in. So we would end up with nothing, right? We would just end up cutting the box in half. That's not really going to work. And so the points over here on this graph don't really make any sense. That means you're cutting past the halfway point. So this part of the graph isn't really helpful. And if you look at it, it continues on forever. So the real absolute maximum would be infinity, right? Because as we continue on, it goes up forever according to our equation. But our equation is really just representing something that we have in the real world. We have this physical box. And so this part of the equation right in here means something to us. And we've got a maximum volume because at x equals 4, this is a relative max, which is why we're investigating functions, why we learned that. So at x equals 4, we have an output of 1024. So that would be what? 1024 cubic inches, right? Would be the maximum volume. I found that you can actually just click on it. You might not be convinced, right? Like maybe that's not the maximum. So there's a couple things that you could do there. Ultimately, you would need calculus to figure out whether or not this was a true maximum or not, because you would want to find out if where the derivative is 0. But if you're in pre-calculus, you're not going to know that. So we're going to design problems that are going to make that easier for you. You could certainly test different points that are really close to it, right? You could do 3.9999 in the table, and then you could do 4. Let's see, you could change this to 4.0111. And as you can see, like at 3.9999, you're at, well, I guess that rounds it, doesn't it? Yeah. You get really close to 1024, but you're not quite there. And then right after it, you get really close, but you're not quite there. So using Desmos, using your graphing calculator, you can start to find maximums. You could just look in the table of values. But as you can see, you're going to use multiple sets of resources in order to solve these types of problems. And it all starts off with just making sense of the problem. What's going on here? Hopefully that helps you get some hints on how to solve some problems and how to work through some of this stuff. Good luck.